Hello students and welcome to the class. Today we're going to dive into Unit 3, Current Electricity, and we'll start with the most fundamental topic of all, electric current. Now this is an absolutely crucial idea in physics, but don't worry, I'm going to explain it in a very simple way that's also perfectly safe for your exams.
Okay, so before we get into any definitions, let's start with a little puzzle. Something you see every single day, but maybe you've never really thought about it this way. All right, just think about it. The little electrons that actually carry the electricity, they move incredibly slowly inside a wire. I mean, we're talking about a speed of just millimeters per second, literally slower than a snail. So how is it possible that the bulb, maybe many meters away, lights up the very instant you flip that switch? It doesn't quite add up, does it? Well, today we are going to solve this mystery.
To solve that puzzle, first we need to get a real feel for what electric current is. Forget the textbook definitions for a moment. Let's build the idea with a simple analogy first, something you can picture in your mind.
I want you to imagine a giant concert hall, and it is completely packed with people, shoulder to shoulder. Now, every single person in this hall is like one electron inside a wire. So, let's make the comparison. The people are the charges, right? The electrons. Suddenly, a fire alarm rings. That's like applying an electric field with a battery. What happens? Everyone starts moving towards the exit. Now, think about it. Any one person is probably walking slowly, carefully. That slow walking speed is what we call drift velocity. But is the rate at which people are leaving the hall slow? No way, because thousands of people are moving at once. A whole bunch of them are crossing the exit door every single second. That rate, how many people exit per minute, is the electric current. So you see, current is not about how fast one electron moves, it's about how many electrons pass a point in a given time.
Okay, so now that you have the basic idea, let's look at the official definition. This is the one you need to write in your exams to get those full marks.
So the NCRT definition says, electric current is the amount of electric charge flowing past a point in a conductor per unit time. You see, it's all about the amount of charge in a certain amount of time. It's a rate of flow. Just like we talked about with the concert hall, it's not the speed of one person, but the number of people passing through the door each minute.
And this is the simple formula that captures that idea. I stands for current, and it's equal to Q, which is the total charge, divided by T, the time it takes. And the unit we use for current is the ampere. So what is 1 ampere? It's simply 1 coulomb of charge flowing past a point in 1 second.
Okay, let's zoom into the wire itself now and see how this flow really gets started. And once we understand that, we'll try a very simple numerical to make sure the concept is locked in.
So here's what's happening. Step 1, in any piece of wire just lying there, the electrons inside are in complete chaos. They're moving around like crazy, bouncing off everything in all random directions. So the net flow is 0. Nothing's really going anywhere. Step 2, but the moment you connect a battery, it creates an electric field that zips through the water almost instantly. This field gives a tiny, gentle, but organized push to every single electron at the same time. And step 3, because of this push, all the electrons, on top of their random motion, start to slowly drift together in one direction. It is this slow, coordinated group movement that we call electric current.
All right, that's enough theory. Let's apply this with a very common, simple question you might see in your board exams.
The problem is this. A wire has a steady current of 2 amperes flowing for 5 minutes. We need to find the total charge that has passed through it. Well, we know our formula is I equals Q by T, so we just rearrange it a bit. Charge Q will be equal to I multiplied by T. But wait, here's where students make a mistake. The time is given in minutes. We must convert it to seconds. Remember, beta, in physics we always use SI units. So 5 minutes is 5 times 60, which is 300 seconds.
And now it's easy. We just multiply 2 amps by 300 seconds, and we get 600 coulombs. So 600 coulombs of charge flowed through that wire. See? It's quite simple once you know the formula and remember the units.
Okay, now for a very, very important part of our lesson. Let's talk about the common mistakes. These silent killers, I call them, because they silently steal your marks in an exam. We need to make sure we don't fall for these.
This is the #1 biggest mistake. So many students think that current is the speed of electrons. This is completely wrong and you will lose marks for it. As we've learned, current is the rate of flow. It's about how much charge is passing per second.
Please burn this into your memory. Here's a simple line to remember. Current measures how much charge passes, not how fast it moves. It's about quantity, not speed.
And this brings us back to our original mystery. The wrong idea is that electrons have to physically run all the way from the switch to the bulb. The correct idea is that the signal to move, that electric field we talked about, travels at almost the speed of light. So the moment you flip the switch, it tells all the electrons everywhere in the wire to start drifting at the exact same instant.
So here's your second memory hook. The signal is fast, but the carriers, the electrons themselves, are slow. It's just like a long pipe full of marbles. If you push one marble in at one end, another marble comes out the other end instantly, even though each marble only moved a tiny bit.
And one last common mistake. Many people think that a bulb or a fan uses up the current. This is not correct. Charge is always conserved. The amount of current that enters a bulb is exactly the same as the amount of current that leaves it. What is getting used up is the electrical energy, which the bulb converts into light and heat. The current itself just keeps flowing.
All right, we're just about done. Let's quickly wrap this up by seeing how this topic fits into the bigger picture of the chapter, and then we'll do a quick summary.
You see, understanding current is the essential first step. It's our starting point. In the next class, we're going to learn about what tries to stop this current, which is a property called resistance. And after that, we'll bring everything together, voltage, current, and resistance, with the famous Ohm's law. So mastering this topic today is the foundation for understanding everything about circuits.
So, let's do a quick revision. What are the key points to take away? 1. Electric current is the rate of flow of charge. I equals Q divided by T. 2. Its unit is the amp. 3. It is caused by the very slow, collective drift of many, many electrons. 4. The signal that makes the move is almost instant, but the electrons themselves are slow. And 5. Current is not used up, it is conserved in a simple series circuit.
And I'll leave you with a final question to think about for our next lesson. If current is just this slow, gentle drift of electrons, then what is actually happening inside that wire that's powerful enough to create so much heat that it glows and produces light? Think about that. That very question will lead us directly into our next topic, which is resistance. Thank you so much for your attention today, and I'll see you in the next